Okay, welcome to this lab session. In the previous couple of sessions, we have seen the free vibration response, and in the coupled pitching and bouncing, we also observed the resonance phenomena in the pitching mode and the bouncing mode. This experiment is again a case of a forced vibration response, but the difference here is that we are going to observe what is typical for a multi-degree of freedom system, and that is mode shape. Okay. So, one way to observe the mode shape, as we have seen in the past, is to excite the multi-degree of freedom system initially with a displacement profile that matches with the mode shape of that particular natural frequency, and then release it so that it executes free vibration response in the pattern of displacements, which is essentially a mode shape. However, that becomes little tricky to get in a multi-degree of freedom system. One of the way of finding out or observing a given mode shape is to excite the multi-degree of freedom system at its one of the natural frequencies. So, the external force excitation should be given equal to one of the natural frequencies, and when you excite the given multi-degree of freedom system at one of its natural frequency, the corresponding displacement pattern matches or is same as the mode shape corresponding to that natural mode. And this is precisely what we are going to observe in this system. So, this particular experimental test setup mimics a multi-floor building wherein we have used these three plates representing the mass of the floors, and the columns are actually represented by these flexible plates, which essentially represents the stiffness, the lateral stiffness of the columns. So, as you notice, this can be treated as the first floor, second and the third floor, and the columns are actually these thin plates. So, the system here undergoes lateral vibration because of the compliance of these thin plates, and the inertia are represented by these three floors. So, that's how this is a multi-floor building system represented simplistically here as a multi-degree of freedom system. Now, because it's relatively very difficult for this system to vibrate in this particular plane, the natural way in which it vibrates, given the kind of excitation, is in the vertical plane, and the motion is sideways of these heavy inertia masses. So, obviously, I can approximate this system to have mass number 1, mass number 2 and mass number 3 connected with spring K1, K2 and K3, and therefore, it is appropriate for us to assume this to be a 3 degree of freedom system. 1 degree of freedom is x1, which is the lateral motion of this inertia, x2 the lateral motion of this inertia, and x3 the lateral motion of this inertia, connected by, as I said, K1, K2 and K3. These are the 3 springs. These 2 plates together represents 1 stiffness and so on. Now, if we want to let it vibrate freely, I can disturb this So, if I want to excite this system into free vibration, I can disturb this, and this is how it vibrates freely. So, this is a free vibration response given to some initial condition. Now, depending upon the kind of initial conditions you give, the ensuing vibration response will be essentially guided by the way you initially excite this multi-degree of freedom system. If we excite this in a way that the displacement at t is equal to 0 of this mass and this mass and this mass conforms to, let us say, the first mode shape, then the ensuing vibration after t is equal to 0 is going to follow the vibration motion, vibratory motion following that particular mode shape. Now, in this case it has definitely moved in the first vibratory mode, the mode 1 displacement pattern. The mode shape number 1 was evident here, and whether that mode, you can actually calculate the mode shape based on the numerical values of the masses and the stiffnesses of these plates. Okay. Now, as I said, it's relatively tough to excite all the subsequent modes. Maybe the first mode might be easier to excite. So, therefore, you can see that this is the first mode that got excited. Getting the second mode or third mode is going to be relatively difficult, because we have to pull and push all these masses in exact proportion corresponding to the second or third mode shape, and then release it, which is as I said, is slightly difficult to initiate at t is equal to 0, and therefore mode shapes, higher mode shapes are hard to obtain by giving initial displacement conditions. And therefore, what we are going to do is we are going to excite this at a frequency matching with maybe the first, the second and the third natural frequency. And when we are exciting this vibratory system at its second, third or first natural frequency, the frequency corresponding to the principal modes of vibration, we expect this entire vibratory system to respond at its resonance or at its natural modes, and the displacement pattern that we will observe at the resonant condition will actually conform to the mode shape corresponding to that particular principal mode of vibration. So, for exciting this, what we are going to do is, this entire building is mounted on a plate here, which is made to oscillate using an electrodynamic shaker in the horizontal direction. So, as you can notice that this bottom plate is connected to the shaker through this connection, and the shaker's plunger keeps oscillating based on the frequency and amplitude with which the electric signal is fed to this exciter. Now, for that purpose, what we are going to do is to use a signal generator here, which is going to generate an electric signal of a given frequency and amplitude, which of course will get amplified using this power amplifier, and the amplified signal is fed to the electrodynamic shaker, so that the shaker oscillates or moves the base plate back and forth at a given frequency. And so that is how we have done here. We have initiated a harmonic signal of a given frequency using this signal generator, fed it through the power amplifier to the oscillator, so that the base motion to the base plate here can be adjusted based on our requirement. So, if this base or the whole vibratory system is excited at its base with a frequency that matches with one of the natural frequencies, the corresponding resonance phenomena is going to be evident, and at that particular resonance phenomena, the displacement pattern is going to conform to the given mode shape. Okay. So, if the excitation frequency matches with the first natural frequency, then the mode shape corresponding to the first natural mode will be evident and will be seen and observed in this multi-degree of freedom system. If you match the excitation frequency to the base equal to the second natural frequency, then the mode shape corresponding to the second natural mode will be observed as a vibration response here. So, we are going to now start scanning past the frequency starting from 1 hertz onwards in the step of 0.1 hertz, and look at where we observe the resonances, and at that resonance condition we are going to observe the way this multi-degree of freedom system vibrates. So, Anuj is going to help us manipulate the frequencies in steps. So, right now the frequency is 1 hertz, right, and this is the frequency 1.1 hertz now. Now, you can see that the amplitudes of vibration here of all the floors have started increasing. At 1.2 the frequency of excitation, the amplitudes have again increased. Now, when we move it to 1.3, you can see that the vibrations are quite strong, and all these 3 floors are moving in phase. You can see that if you play this video in slow motion, you may observe that all the 3 floors are moving in phase, and if this is the resonance corresponding to the first natural mode, then any increase in the excitation frequency will further reduce the amplitude of vibration. So, if we increase it to 1.4, what we can notice that the amplitudes have slightly dropped, and if you take it to 1.5, so you can see that the amplitudes of vibration of all the floors have gone down considerably. Now, if you come back from 1.6 hertz and take it closer to 1.3, we can definitely say that 1.3 hertz is the frequency at which the first resonance has been observed. And yes, so this is the frequency of 1.3 hertz, and you can see that the whole building is moving back and forth in phase. All the masses move in phase, and if you do the numerical calculation of this as a multi-degree of freedom system, modeling this as a 3 degree of freedom system, it is possible to show with the numeric values of these masses and the stiffnesses which we shall provide you. You will see that this amplitude, if it is normalized to one value, 1 unit value, this is let us say 0.7 or 0.8, and this one will be roughly 0.4 or so, and all of them are positive, meaning that when this moves 1 unit, this moves by 0.8 units, this moves by 0.4 units, and this of course will be 0. So, now this is basically is indicating the first mode response, and this is the resonance that we are observing here. Okay. When the system vibrates at its resonance, the mode shape corresponding to that natural frequency is exhibited. So, the operational deflection shape which we normally talk about is actually matching with your mode shape corresponding to the given natural mode. Yes. So, now we will shift our frequency in steps and check at any other resonance that we observe. Now, obviously, this is a 3 degree of freedom system, and we expect 3 different resonances here, and so let us see whether we get another resonance by increasing the frequency and scanning it past the second natural mode. Can you take it past? Okay, so this is the second mode that we are observing, and in the second mode, if you look at closely, this floor moves on this side, and when it is going in this direction, the first floor goes in the opposite direction, and if you watch it very closely, this floor is almost having a 0 displacement, meaning that this displacement is, if it is rightward, this displacement is leftward, and if you draw the mode shape, it will have a node somewhere closer to this plate. This plate is not exactly 0, it has some motion, but that motion is very small compared to these two motions, and so you have +1 here and maybe some amplitude here that you can find out through numerical calculation, but you expect to get a 0 displacement location between this and this, because this is moving this way and this is moving this way. So, there will be, if you join all of these, there will be some position where the displacement is going to be 0. So, that is how the second mode appears here. This is a resonance corresponding to the second natural frequency. Now, we can check that by reducing the frequency whether the amplitude drops, or by increasing the frequency the amplitude drops. Yes, it is quite clear that at 4.1 hertz the amplitudes have significantly reduced. Maybe you can increase it further and see whether the amplitudes reduce. So, obviously, the amplitudes compared to about 4 or 4.1 hertz have significantly dropped. Oh, this is increasing, right? So can you take it to 4.3? Let us check. Yeah, 4.4. So this is 4.5 hertz. Amplitudes are less as compared to at 4.3. Can you go back to 4.3? And probably here we expect large amplitude. So it's very difficult visually to confirm what is the amplitude, whether it is highest at 4.3 or 4.2. That we can find out by using a sensor and then taking the data. But visually, either 4.1, 4.2 or 4.3, these are the two frequencies at which we are visually seeing larger amplitudes of vibration. Reduce it further. Let's see. 4.2, 4.1. Yeah, 4.3 appears to be the large one, as well as 4.1. 4.0, if you can take it to 4.0, I think that's the amplitudes are less as compared to. Yeah, probably 4 is the frequency that we are looking at. There is definitely a much larger amplitude, and you can see that this plate is moving this way, this plate is moving this way. So this plate reaches its maximum peak value rightwards. At the same time, you will see that this plate is going to reach its maximum value on the left side. So the mode shape is like this. This is 1 unit amplitude, and then you can see that there will be maximum amplitude on the left side, and then going back to 0 here. So this is how the mode shape would look like. There will be a node position here, somewhere here nearby this plate, and that is the reason this plate has much lower amplitude as compared to this one and this one. That's how you can figure out or verify the mode shapes corresponding to individual natural frequencies. We are of course not getting a free vibration response. We are getting a forced vibration response, but the mode shapes are basically getting inferred from the operation deflection shape corresponding to the resonance points. Okay, so this is the second resonance or a second natural frequency, and that the kind of the mode shape that we are observing is basically going to be corresponding to the second natural frequency. Yeah, we can now 6, take it closer to 6 hertz. Okay, so now we have increased the frequency to 6, close to 6. Now this is 6.2, this is 6.1, and maybe you can reduce it further just to check which one is the frequency corresponding to larger amplitudes. Yeah, I think this one is 5.8 is the frequency that we are observing. 5.9, can you take it to 5.9? Yeah, you can see that now. You observe here the middle plate is now giving largest amplitude. Visually I can see that this plate does exhibit larger amplitude as compared to this one and this one, and if you run this video in slow motion, you will realize that when this one goes on the left side, this one and this one, they go on the right side. So the motion of this middle plate is out of phase with respect to these two plates, and these two plates will be in phase. Now what does that mean? If this goes on this side, this goes on this side, and this goes on this side, if you join the points of displacements of each of these masses, there will be a node point in between these two plates, because both of them are in opposite phase, and since this and this are also in opposite phase, there will be another node point in between the motion of these two plates, which means that in the first mode we never observed any node point between this plate and the top plate. In the second mode we observed a node somewhere closer to this plate. There was only one node. And in the third mode, natural mode shape, we see now a possibility of two nodes being observed. One is between this one and this one, and the other one is between this one and this one. So one node gets added in general when you go to a higher mode of vibration. So again, this is a resonance. This is not strictly or theoretically a mode shape, but the operation deflection shape or the displacement pattern of this multi-degree of freedom system when it vibrates at when it vibrates at its resonance, the vibration displacement pattern is actually representing the mode shape corresponding to that natural frequency. So 5.9 hertz is what we have observed, a major resonance here, the third natural frequency related resonance, and at that resonance this executes largest amplitude. This one's little smaller, this one little smaller compared to this, and this one are out of phase, this one and this one are out of phase, and therefore there is a node point between the motions of these three different plates. Okay, so this is how is the mode shape in a multi-degree of freedom system that we are observing. Okay, now let's go back to the first mode. Okay, and if you remember, there was a concept of a vibration absorber, and I think the video of the vibration absorber was also shown in the discussion of the undamped vibration absorber. Now, if this frequency is 1.3, where large resonant vibrations of this building is being observed, we said that if you attach an auxiliary system, the absorber, okay, which has the natural frequency tuned to the natural frequency of this vibratory system, the parent vibratory system, the amplitude of the parent system can be brought to 0. Now, what we are going to see is, I am going to attach this as a pendulum. It is a very simple structure, has a hinge point here which I can connect it at this point, and this is a very simple a pendulum with a mass here. The distance between this fulcrum point or a hinge point and the center of the mass should be adjusted in such a way that the natural frequency of this pendulum matches with the natural frequency of this system, the parent vibratory system. Okay. We have measured this distance, and this distance has been adjusted in a way roughly about 14.4 centimeters. With 14.4 centimeter, the natural frequency, all of you are aware, for a simple pendulum is square root of G by L, and if you work this out, 1.3 hertz, the L corresponding to 1.3 hertz turns out to be 14.4 centimeters. So, I am basically ensuring that the pendulum length is about 14.4 centimeters, and with that 14.4 centimeters of length, this pendulum should be able to absorb the vibration of the parent system. So, what I am going to do here is to attach this pendulum and see if the parent system vibrations are brought to 0, and you can see that compared to when the pendulum was not there and the system was vibrating at its first natural mode, the amplitudes were very large. By attaching this absorber, you can see that the vibrations are of course not exactly 0, but they are much smaller as compared to when it was not there. So, this vibration absorber does its job of reducing the vibrations of the parent vibratory system, and you can again note that the amplitudes are substantially large at its first natural frequency, and by tuning the pendulum's parameter like the length, I am ensuring that the pendulum natural frequency is 1.3 hertz, which is the first natural frequency of this building. And now the moment I attach this pendulum, the pendulum swings with large amplitudes, but the building's vibrations can be brought to 0. So, the vibrations, you can see that the building's vibrations are almost becoming 0. Okay. If you tune it perfectly, if you shift the mass here and there, this is an approximate position of the mass, but then you can see that if I remove this, the vibrations are much larger than what it was when the pendulum was not there. Okay. So, this is how the vibration absorber works for a multi degree of freedom system as well. Alright. So, what we have learnt here in this experiment, we have seen the mode shape in action. It is not by exciting the vibratory system at it with the initial condition matching with the mode shape and the subsequent vibration at the natural mode, but we observe the mode shape by exciting the system at its resonance, and for that we excited the base of this building with a frequency that matches with either the first mode natural frequency, the second one and the third natural frequency, and when it is excited into resonance, at resonance we observe the displacement pattern, which is actually the mode shape. So, in the first mode all the plates moved in sync in only one direction. So, that means they were moving in phase. In the second mode, this plate and this plate were moving in out of phase, and there was a node location somewhere close to this plate, and in the next, that is the third mode, we observed two node position, one between this and this plate and the other one between this and this plate. Okay. So, this is how the mode shapes are observed in this particular building vibration experiments. Okay.